Now we're going to go over the review for the Unit 3 test, energy transfer and storage. The first page is just a reading, basically, the ideas that are covered in Unit 3. Kinetic molecular theory, everything's made of little particles that move, and in the solid phase they just basically vibrate. If you heat them up enough, they break that little magnetic bond and they start to slip around each other into the liquid phase. Once it's a liquid, you can increase the speed of the particles up to the boiling point, whatever the substance is, and once you reach the boiling point, the particles are now gaining energy not as thermal, not as a temperature change, but as a phase change. They're actually pulling the magnets apart, separating them into the gas phase. And then once it's all in the gas phase, you can heat the particles up and make them move faster again. And they're stored either as phase or as thermal and transferred as heat. Go to the second page. This review is basically just one problem, and this is it. Calculate the total energy, the total Q, that needs to turn a beaker of 1,000 grams of solid water ice at negative 25 degrees Celsius until it becomes a gas at 135. So we've got to find ourselves on the curve. It starts at negative 25. Again, for water, that means the freezing or melting point is 0, the boiling point or condensing point is 100. So negative 25 is down here somewhere. And it says we're going to heat it, so we can heat the solid. Once we get up to the melting point, all the energy we put in will not heat it and it won't change its temperature. It's being stored as a phase to change it from solid to liquid. Once it all becomes a liquid, the energy is now being stored thermally, and the temperature goes up. Once we get to the boiling point, the temperature won't rise anymore because all the energy is being stored as phase change to get those particles to become a gas. Once it's all gas, we can then raise the temperature again, and it says up to 135, so that would be right around there. It's about 135 degrees, and this is negative 25. And now we want the Q, the total energy. We can see that we're in all 5 sections, so we're going to use all 5 of these equations. All right, and you want the total, so we'll just add them up. In the solid range, remember, it's all just one equation, just with different constants. In the first section, the solid section, the energy is mass times the heat capacity of the solid times the temperature change. So that's 1,000 grams. Specific heat of the solid is 2.1 joules per gram degree Celsius. The temperature change, well, it starts at negative 25, and in this section it goes up to 0, so that's a 25 degree temperature change. And that, if you get out your calculator, is 52,500 joules of energy. The grams and the degrees Celsius cancel. For this next section, there's no temperature change. It's in this case, the melting phase. And that equation, it's the same equation. Q is m times a constant, and the constant is the heat of fusion. No delta T, because there is no delta T. So it's just 1,000 grams times the heat of fusion, which is 334 joules per gram. Grams cancel. 1,000 times 334 is 334,000 joules. So we've gone from heating the solid from negative 25 to 0, melting it, took another 334,000, and now we'll do the equation for raising the temperature of the liquid. Same equation, Q is mass times the constant, in this case the liquid heat capacity, times the temperature change. Still 1,000 grams. V1 is 4.18 for water, joules per gram degree Celsius. And then delta T goes from 0 to 100, so that's 100 degrees Celsius. So 4.18 times 100 is 418, times 1,000 is 418,000 joules. So 52,500 to heat the solid, 334,000 to melt it completely to a liquid, 418,000 to raise it 100 degrees to the boiling point. And now the equation for actually turning it all into a gas is mass times heat of vaporization. So it's 1,000 grams, still same mass. Heat of vaporization is 2260 joules per gram. So that's 2,260,000 joules. And that's what it took to just vaporize the water. The last section here is where we heated the gas. Same equation, but this case, the gas constant, the gas heat capacity times temperature change. So it's the same 1,000 grams. The heat capacity for gas is 1.996. For ease, I'll put 2. And the temperature change, well, it says it went up to 135, so 100 to 135 is a 35 degrees Celsius change. So it's 2 times 35 is 70, times 1,000 is 70,000 joules. And then all you have to do is take all of these values and add them up. So it took 3,134,500 joules to completely heat 1,000 grams, a liter of negative 25 ice, all the way up till it was a complete gas at 135 degrees. The next part of this is to do a particle diagram for each section. So we're talking about a particle diagram for each one of these 5 sections of the heating and cooling curve. The solid, you can do whatever you want. You can consider the box to be a beaker. So the solid is just a cube like that. It holds its form, and we're going to have, I'll draw 10 particles, just because that's a nice arrayed order. And they do have speed. They are vibrating. So I'll give them a whooshy for each particle. The solid to liquid, well, this is where we had part of it was liquid and a little bit left was solid. So remember, in this region there's no temperature change, so we'll keep the temperature constant. And where it was all a liquid, where we were heating it up, you could draw 2 particle diagrams if you want, one where it was cold and one where it was moving faster. But it's all liquid, and I will show still my 10 particles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just moving faster, because I'm heating them in this range. And then a gas, well, in the liquid to gas, we've got some of it liquid, some of it gas. So I'll show that I'm boiling it off. And again, there's no temperature change in this region, so I'll keep the temperature when it was for my 10 particles. And then the last phase, it's all there, it's just been changed, but it is certainly going faster now. This is a region where I'm heating the particles up. And then the last bit of this is where we're drawing an LOL chart for each of the 5 regions. And the last page, it looks like this. You've got 1 for each region. So we're going to do an initial, final, initial, final, initial, final, initial, final for every section of the heating and cooling curve. So we'll start up here. Obviously, we're a beaker of ice. And this is for the section when we start down here. And remember, in our system, it's A to B to C to D to E and up here to F. So this is our A to B region. And we start off as a below 0 solid, and we end up as a 0 solid. So it's already labeled. It starts as a solid, and it ends as a solid. Starts below 0 and ends at 0. Okay? And this is 1.5 bars, ends as 2 bars. So we must have gained 0.5 bars. We must have gained that much. So I'll show a half a bar coming into the system. Now the key point of this is that we went from A to B. In the second LOL chart, we're going from B to C. So if we ended with B and start with B on the next one, that means that these should always be the same. So B starts as a 0-degree solid and ends as a 0-degree liquid. Remember, it's melting from start till it's completely melted at C. So this is our B to C region. We're going to start with a solid but end with a liquid. This is the melting phase. Melting means solid to liquid. It starts at 0, and again, there is no temperature change all along that plateau there, so it should remain at 0. So we started with 2 bars, we ended with 3 bars, 1 bar must have come in to the system. And again, this is A to B, B to C, and this will be C to D. This will be our warming of the liquid. So B to C, C to D should, so wherever we ended with in the second one should be our starting point in the third one. So these should be the same here. And it warms. It remains a liquid, but it warms up. And I'll go ahead and give it 3 bars because we like to think of 2 bars as room temperature. So I'll give it 3, and we have 2 bars coming into the system. Wherever you ended, A to B, B to C, C to D. So D should also be the same conditions, and it goes from a hot liquid to a hot gas, because this is the boiling region. So we'll temperature the same. We'll go from 5 to 7. We should have 2 bars coming into the system. This is E, so wherever we end at E, we should start the same spot. And all we do in this region is heat it up. It gets hotter, but it's still a gas.